All right, guys, welcome to lesson 6.1. Unit 6 is readdressing the concept of integrals. So far this year, we've only talked about the rules of integrals, like how to do a basic integration problem like this. You guys will remember, like, the integral of 2x is x squared plus c. Okay, we did that earlier this year. That's just the basic rules of integrals. But Unit 6 is kind of like, what are the concepts behind integrals? What makes an integral what it is? What do integrals represent? Okay. Our last unit of the year will be Unit 7, and in that case, we're talking more about, okay, so what do mathematicians do with integrals? What kind of applications do they have? We might even start getting into some of those here in this particular unit as well. But for today, let's go ahead and start off with something called Riemann sums. So today we're going to learn how to estimate area under a curve using what's called a right and left-handed Riemann sum. And then using those, we're going to determine whether it's an overestimate or an underestimate. Okay? So here's a Riemann sum, basically. It's a way to estimate area under the curve using rectangles. Now, this line right here is f of x. That's my function. And the area under that curve can be represented by a shaded region, which I'll just loosely shade in here. So what is the area of that red region? Well, there's no geometry that we can do for that. That's like a weird curved shape. And other than circles, geometry doesn't really help us much when it comes to trying to find area of curved shapes. So how can we do this? Well, we can't find the exact area under the curve using geometry, but we can find something pretty darn close. And the way you do that is by drawing a whole bunch of rectangles underneath of the curve. Okay? And then you find the area of the rectangles just using basic geometry. And as you guys can see, that'll get you kind of close to what the area under the curve is. We'll just be missing the area that's accounted for by some of these little white triangles here. But the green area is going to be pretty close. Now, in case you guys don't remember, integrals tell you the exact area under a curve. So the sum of all these rectangles areas added together will be approximately equal to the integral from x equals 0 to x equals 2 of the integral of this function, and that's how we write it. So the integral tells you the exact area under the curve. The rectangles doing the geometry will get us close. And today we're going to be doing the geometry side of things. So there's 4 different ways we're going to estimate area under the curve using geometry in this class. One way is with a left-handed sum. They call it that because for each rectangle, the left corner is what's touching the curve. A right-handed sum is where the right corner of each rectangle is touching the curve. A midpoint sum is a sum where the rectangle's midpoints are touching the curve. Now, left-handed sums and right-handed sums can be overestimates or underestimates. Now, in this particular case, as you guys can see, this is an underestimate of the area because we're missing some area under the curve. Whereas in this case, the right-handed sum gives us an overestimate because the rectangles are sticking out above the curve. And as you guys could probably imagine, a midpoint sum is actually going to be a better estimate because, yeah, there's a little bit missing on this side, but there's also a little bit over on this side, and those two pieces might cancel each other out. So you could end up with an area that's pretty darn close to the actual area under the curve. Another way to get pretty close to the area under the curve is with trapezoids. And that's our 4th way. There's geometry formulas for finding the areas of trapezoids. And trapezoids work really nice because they don't have to be like this and give you either too much or too little. Instead, they give you a straight line, which still might create some error because it doesn't follow the curve exactly, but the diagonal line definitely follows the curve closer than a rectangle would. So using these diagonal lines, which creates trapezoids, is another way to get a better estimate of the area under the curve. Now, as I mentioned, when it comes to right-handed sums and left-handed sums, they could be either overestimates or underestimates. Now, on the slide I showed you earlier, I don't want you to get the wrong impression, think, oh, anytime it's a left-handed sum, it's going to be under, and anytime it's right, it's over. That's not true. It's actually an interaction of two separate factors. It depends on whether you're doing a left-handed sum or a right-handed sum, but it also depends on whether the function is increasing or decreasing. So if you have a function that's increasing, then a left-handed sum will give you an underestimate. But if your function's decreasing, the opposite happens. In that case, if your rectangle's left-handed corner is on the curve, the right-handed corner is going to go above it and you end up with an overestimate. And the opposite happens with right-handed sums. With a right-handed sum, if your function's increasing, then you get an overestimate. But if your function's decreasing, you get an underestimate. So it's really an interaction of two separate variables, two separate factors. Are we doing a left-handed or right-handed sum? And is my function increasing or decreasing? All right, here's some other terminology that's associated with the concept that we're addressing. All right, the estimate of the area under the curve is what we call a Riemann sum, because the guy who first came up with this was named Riemann. If the sum is an underestimate, sometimes it's called a lower sum. If it's an overestimate, sometimes it's called an upper sum. So the first thing I want to practice with you guys is teaching you how to draw these rectangles. Believe it or not, it's actually a little bit trickier than it might seem. All right, so here we go. The reason why it's tricky is especially whenever it goes underneath of the x-axis, things get a little bit interesting. All right, so let me show you guys how to draw these curves. Let's start off with a right-handed Riemann sum. So I want to start off with something easier before I get to the examples that are in our notes. And you guys don't need to write this. I want you guys just to watch, okay? So this is just practice on how to draw it. So let's draw a right-handed Riemann sum. Now what that means is I want rectangles, and I want my rectangle's right-handed corner to be touching the curve. So the first thing we're going to do is we're going to start with the right endpoint. And starting from that right-handed endpoint, I'm going to draw a horizontal line going left. So let me show you what I mean by that. I'm going to start by drawing a horizontal line from my right-handed endpoint. I'm going to go left until I get to the next dot, and then I'm going to stop, just like that. And I'm going to keep doing that from this dot over until I get to the next spot, from this dot over to the next spot, from this dot over to the next spot, from this dot over to the next spot, and then from this dot over to the last spot. Okay? So you start on the right-handed endpoint, and you're going to draw a horizontal line going to the left. The next thing you're going to do is you're going to draw vertical lines to the x-axis. Okay, so starting from the right-handed endpoint, vertical line, straight down, straight down, straight down, straight down, straight down, straight down, and there you go. So you end up with a bunch of rectangles like that. And so now, at this point, which I'm not going to do this part, but what you could do is you could find the area of each rectangle, and you could add the area of each one of these rectangles together, and that would roughly estimate for us what the area under this weird-looking curve is that we have. And this is a right-handed sum, because each one of my rectangles is touching the curve of f of x on their right-handed corner. Okay? So that's a right-handed sum. Now, let's say we want to do a left-handed sum. And once again, you guys aren't writing this, you're just watching for now, because you're going to get a chance to write some down in a second. So let me show you one more. So now this time I want to do a left-hand sum. Now, if you want to do a left-hand sum, you're going to do the opposite of what we did with the right-hand sum. Instead of starting on the right side and going left, we're going to start on the left side and go right. So let me show you what I mean by that. I'm going to start with this left dot and go to the right till I get to the next dot. And just kind of keep doing that. And what I'm drawing here is just the tops of every rectangle that I'm going to have. You don't use the last dot though. You're not going to go this way because now you're adding area past the point that you wanted to go. We don't go past that point. So you don't draw a horizontal line on your last point, just so you know. I didn't do that on the last one either. And then once again, you're just going to draw a vertical line straight down from each dot. Now I'm not going to draw a horizontal line down from here though, because we're not using that last dot. Okay, so that's the idea. And now these rectangles estimate for us the area under the curve. Okay, from a left-handed endpoint. So that's the idea. So if it says right-handed sum, you start on the right side. If it says left-handed sum, then you start on the left side. Now let's go ahead and do the examples, and this is where you guys can start writing with me. All right, so use a right-handed sum, so I'm going to underline that, to estimate this integral. Now remember, an integral means area under the curve. Notice that we're going from -3 to 0, so I'm going from here to here. Those are x values. And we're going to estimate the area under the curve. Now the area under the curve, don't draw this, but just pay attention for a second. The area under the curve is really this little triangle with the bended hypotenuse and then this little half parabola piece here. That's the real area under the curve. But we're going to be estimating this area using rectangles, okay? A right-handed Riemann sum. All right? Now, let's go ahead and do a right-handed Riemann sum. So I'm going to start on the right point, and I'm going to draw a horizontal line going left. Then I continue that process. And you don't use the last point. So I'm going to leave that one off. Then what I'm going to do is I'm going to draw a vertical line from the point to the x-axis. So from here to here, from here to here, from here to here. Now this one's interesting. It's already on the x-axis. So what we have there is a flat rectangle. In other words, it's just a line. That rectangle doesn't exist because it's flat. It's right on the line. And since we're not using this dot, we're done. So this one's Riemann sum is done. Okay? So now the next question is this an upper sum or a lower sum? In other words, is it an underestimate or an overestimate? Well, for that, we want to go back to this last slide that I shared with you. Is our function increasing or decreasing? We know it's a right-handed sum. Well, our function looks like this, right? So it's increasing. So when you have an increasing function with a right-handed sum, it's always going to be an overestimate. Always going to be an overestimate. So in this case, it would be an overestimate. Now let's go ahead and figure out what this area is, by the way. What's the base of this rectangle? It's 1. What's the height? It's 4. So what's the area of that rectangle? It's 4. What's the area of this rectangle? The base is 1, the height is 3, so it's 3. So we have an overestimate of the area under the curve from -3 to 0 using a right-handed sum, and our overestimate gives us an area of approximately 7. All right? Let's do another one here. Let's go ahead and do a left-handed sum. Same problem, we're just doing a left-handed sum now. So this time we're going to start with the left-handed dot. We're going to draw a horizontal line, draw a horizontal line, draw a horizontal line, and we leave out the last dot. and then we draw lines to the x-axis. But now that's funny because watch. Since this one is below the x-axis, when I draw my vertical lines, it's going to go up to the x-axis. So once again, we have one rectangle that's flat because it's right on the x-axis, but I do have one over here and one over here. Now, is this an overestimate or an underestimate? Well, once again, let's go back to our chart. It's still an increasing function, but this time we're dealing with a left-handed sum. When you have a left-handed sum in an increasing function, it's an underestimate. So we're dealing with an underestimate here of the area under the curve. Now let's find our area. So we have an underestimate of the area under the curve, which is represented by this integral. Let's see what it is approximately by finding the area of these rectangles. All right, for this rectangle here, the base is 1 and the height is 3, so that's 3. How about this rectangle over here? We have a base of 1 and a height of 5. So you might think it's 5, but now this is something I'm going to ask you guys to pull out from your memories from way back in August. What do we remember about area that's underneath the curve whenever it's under the x-axis? When your area is under the x-axis, that's actually a negative area. So we're going to put a negative 5 there. So the area under the curve is negative 5 plus 3, which is negative 2. Okay? So over here, my overestimate is 7. My underestimate is negative 2. So I know the actual area of this under this curve is really going to be somewhere in between 7 and negative 2. So as you guys can see, this is not a very good estimate, but that's okay. I'm not too worried about getting great estimates right now. I just want to make sure of two things. Can you draw your rectangles, and can you find the area estimates and decide whether they're over or unders? All right, so here's one for you guys. Pause the video here, and I want you guys to do a right-handed sum for this graph on the left, and then I want you to do a left-handed sum for the graph over here on the right, and I want you to decide, is it an upper sum or a lower sum, and then I want you to also include what you got for the areas for each one. So pause the video, and when you unpause it, you can check your work and you'll see the solution. Okay, so the first thing I want you guys to check on is, did you draw your rectangles correctly? Stop here and take a look at your rectangles for the right-handed sum and for the left-handed sum. The next thing I want you guys to check is make sure you determined correctly whether this is an underestimate or a lower or an overestimate. In this case, we have an underestimate because it's a decreasing function with a right-handed sum. So this is an underestimate. For this one over here, we have an overestimate because it's a decreasing function with a left-handed sum. All right? So in other words, this area that we're estimating is slightly too low, and this area that we're estimating over here is slightly too much. So we know that the actual area under the curve is somewhere between negative 10 and negative 1. All right. Next, I want you guys to make sure you actually got the areas right. For this one, I get negative 10, and for the one on the right, I get negative 1. And that's because I just found the area of each rectangle that I drew and added them up. So the one on the left, the rectangles add up to 10, and the one on the right, the rectangles add up to negative 1. Remember, the area when it's under the curve is a negative area. Okay? So that's the first task for the day. Just making sure you know how to draw a Riemann sum, how to determine whether it's an underestimate or overestimate, and then using the geometry to actually calculate the area. So now we're going to deal with another question. And the only difference between this question and the other one is that I didn't give you the graph yet, and you just have to make the graph yourself. So it says for each problem, use a left-handed Riemann sum, so that's important, you might want to underline that, to estimate the area under the curve. So what's my curve? My curve is f of x, and I'm starting at x equals 0, and I'm ending at x equals 9, and the question is, what is the area underneath of that curve? Okay? And we're going to be estimating that area using a left-handed Riemann sum. So step 1, draw a graph. Here we go. We're going to plot all the points that they give me. My first point is 0, 4. My next point is 3, 2. My next point is 4, 3. My next point is 8, 4. And my last point is 9, 5. Now, I don't know how to connect these dots, and it doesn't really matter how I connect them. In fact, you don't even have to connect them. Maybe my graph looks like this. I don't know what the graph looks like. I'll just go with that for now. The reason why we don't know is because, I mean, there's a lot of ways you can connect these dots, right? I mean, couldn't we do this also? I mean, there's a lot of ways to connect those dots. We don't know. I'm just going to go ahead and connect them in the shortest way possible, like that, and there's my graph, okay? We don't know what f of x looks like, but we do know those 5 dots. All right, so that's step 1, sketch a graph. All right, step 2, put your Riemann rectangles. We want a left-hand rectangle, so draw the left-handed Riemann rectangles. So we're doing a left-handed sum, so I'm going to start with the point on the left, and I'm going to draw a horizontal bar until I get right to the next point, and I pick up from there and do another one. And we don't use the last point. And then for the right and left-handed endpoints of each of those horizontal bars I just drew, we're going to draw a line straight to the x-axis. And that way we end up with rectangles. And this was supposed to be at 9, so try to get these things to land right where they're supposed to. It's supposed to be at 9. Okay, there we go. All right, step 3, we want to calculate the area. And that's pretty easy. We just want to find the area of each one of these rectangles. So my first rectangle has a base of 3 and a height of 4, so that's an area of 12. My next rectangle has a base of 1 and a height of 2, so that's 2. My next rectangle has a base of 1, 2, 3, 4 and a height of 3, so that's 12. And my last rectangle has a base of 1 and a height of 4, so that's 4. And then we just add all those areas up to get our area under the curve. So 12 plus 2 plus 12 plus 4 is going to be 24 plus 6, which is, I guess, 34. Now in this case, I'm not going to say whether it's an overestimate or an underestimate. And the reason why is because this function is not just decreasing, and neither is it just increasing. Here, from here to here, it's decreasing, but from here to here, it's increasing. So we can't really say whether this is an underestimate or an overestimate because the function's not strictly increasing or strictly decreasing. So we can't say overestimate or underestimate. But what we can do is we can say, okay, cool. That means the integral of f of x from 0 to 9, which is the exact area under the curve, should be approximately equal to 34. If I added that up right, I wonder if I'm doing that right. Let me double check over. 24 plus 6. Oh, no, it's 30. My bad. It's not 34. It's 30. So the area should be approximately 30 square units. Okay? So in this case, we just had to turn the table into a graph first. So let's go ahead and throw one of these at you guys. So go ahead and pause the video and try this one. Notice this time, though, you guys are doing a right-handed Riemann sum, so pay close attention to that. And you can ignore these instructions because same situation applies you're not going to be able to tell whether it's an upper sum or lower sum. All right, when you guys unpause the video here, we will show you the solution. Okay, and here is our solution. Let you guys look at that. Make sure your rectangles match and the area of each one and the total area matching the integral there. Now, before we go on to example 3, I want to show you guys a shortcut that exists. And the shortcut is a shortcut because you don't actually need to draw this graph. You can actually get the answer rather quickly by just looking at the table. So, for instance, I want you guys to notice that my first rectangle has a height of 4, and that's because my first rectangle on the right side has a 4 for a y value. The next rectangle has a height of 6. The next one has a height of 5. The next one has a height of 3. The next one has a height of 2. And we don't use the last height. Remember how we leave the last dot off, but we also leave the last height off in the table. Now, what about the bases of our rectangles? Well, I'm going from an x value of 10 to 9, so that's a width of 1, right? So the distance between these two is 1. The distance between the next two is 6, and that's why this next rectangle here, going from 9 to 3, has a base of 6. So you can see your bases and your heights by just looking at the table, actually. You don't need to graph it. So if you just find the distance between each x value, those tell you the bases of your rectangle. And if you look at the y values, that tells you the heights. But the trick with the heights is that if you're doing a right-handed Riemann sum, you include all the heights on the right, but you leave the one on the left off. The opposite is true if you're doing a left-handed sum. So the areas of the triangles will be base times height. 1 times 4 is 4. Base times height. 6 times 6 is 36. Base times height is 5. Base times height is 3. Base times height is 2. And lo and behold, these are the same numbers that we have over here. So you don't actually need to graph the thing. You can actually see the bases and heights of your rectangles by looking directly at your chart. So let me show you the shortcut here on example 3. All right, so here are my bases. 0 to 2 is 2. 2 to 5 is 3. 5 to 9 is 4. And 9 to 10 is 1. I'm going to label those as the bases of my rectangles. Now, you got to pay attention to the subtle detail here. We're doing a right-handed Riemann sum, so I'm going to start on the right side. This number is a height, this number is a height, this number is a height, and this number is a height, but this one is not a height. You always leave off the last one. And so we have our bases, and we've got our heights, and you just multiply them. 1 times 1 is 1, 4 times 2 is 8, 3 times 1 is 3, 2 times 0 is 0, which, by the way, that means that's one of those flat rectangles. And then you just add them all up, and you get 12. So this integral is approximately 12 if we use a right-handed Riemann sum. So let me let you guys try practicing one of these shortcut methods where you don't have to draw the graph. So pause the video here and give this problem a try, but I do want you guys to notice that we're doing a left-handed sum. So your heights are going to start here. These are your heights. And you're not going to use the last one on the right. That's the only difference. But go ahead and pause the video here. When you unpause it, you'll see the solution using the shortcut. And there you go. This is a very helpful thing. These are very common FRQ questions, so you'll definitely want to know this shortcut. It's very helpful. All right. Well, let's continue our journey and look at some more types of questions. Example 4. Use a right-hand Riemann sum, but notice there's something different here, of 4 equal subintervals to estimate this integral. Now, basically what this means, 4 equal subintervals, is that means they only want 4 rectangles. That's what they mean. They only want 4 rectangles in this problem. But the thing is, as you guys can see here, if we just go with our shortcut, that's going to be 2, 2, 2. They all have the same base. How many rectangles is this, though? That's a lot of rectangles. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 rectangles. But I only want 4. Okay? So what that means is instead of drawing we're not going to draw the picture. We are going to use the shortcut. But, you know, if we have 8 points, let's just say our 8 points look like this. Instead of doing a right-handed Riemann sum at every dot like this, we're actually going to do it at every other dot. So maybe like this. And that way we're going to end up with 4 rectangles instead. Okay? So sometimes they specify that they only want a certain number of rectangles. So let's go ahead and take a look at how do we do that. Well, what you're going to do is you're going to take your last x value, which is 12. You're going to subtract from it your first x value, which is -4. And we're going to divide it by 4, the number of rectangles we want. Okay, and that's going to tell us the base of each rectangle we actually want. So my last x value is 12. My first x value is a -4. And we want 4 rectangles. That means each rectangle needs to have a base that is 4 units long. So if you take the last x value, subtract it by the first x value, and divide by however many intervals that they want, that's going to tell you how long the base of each rectangle is. So if I'm going from -4 to 12, and I want to divide that up into 4 equal rectangles, then that means each rectangle would have to have a base of 4 units long. So instead of going from -4 to -2, I'm going to go from -4 to 0, because that's a base of 4. And then from 0 to 4, that's a base of 4, and so on. And you'll notice that we don't really care about these middle numbers now, do we? We only care about the endpoints, the left and the right-handed side of each rectangle. So we don't really care about the midpoints anymore because they're not really being calculated into the problem. So I know that each rectangle now has a base of 4. Now, since we're doing a right-handed Riemann sum, and we're ignoring all these middle ones because they don't matter, they're not part of our calculation because we're skipping that one, let's start with a right-handed Riemann sum. So here's my first height, here's my next height, the next height, the next height, and we always leave off the last height. So it's 4 times 13 is 52. 4 times 9 is 36. 5 times 4 is 20. And then 4 times 1 is 4. And by the way, on the AP exam, you don't have to add those together. Just leave it like that. If you're doing a free response question, there's absolutely no reason to add those together because they really don't care about your ability to add. They just want to know that you know how to do calculus. And this shows that you do. So I'm not going to take the time to add those up. Why would I? It's pointless. But let's review for example 4. What made example 4 special is that they wanted us to create a certain number of rectangles. So you take your last x value and you subtract from it your first x value and you divide by however many subintervals that they want. And that will tell you the base of each rectangle. So starting on the left, add that much every time. And that will tell you which pieces to ignore. And then once you've done that, just do it the way we have been. All right? So let's see how you guys do with one of these situations. Now, before we begin, I need to make a slight change. This is supposed to say 3, all right? But go ahead and pause the video here and try to do this now. Keep in mind, you're doing a left-handed Riemann sum of 3 equal subintervals. When you unpause the video, I will show you my solution. All right, and so here's our final answer. Notice I just left it unsimplified again, but maybe you simplified it. If you did, you would get 60, but that was not too hard to add together. Anyway, so here it is. So you take your last x value and subtract from it your first x value and divide by the number of subintervals that they want. And that tells me that each rectangle needs to have a base of 2 spaces in length. So starting on the left side, I'm going to add 2, and that takes me to 0. And then I'm going to add 2 again, that takes me to 2. And then I'm going to add 2 again, that takes me to 4. And anything between those gets ignored. After that, we just calculate the area the way that we have been. We're doing a left-handed sum, so we take the 9, the 6, and the 15, but we ignore the 22. Then we multiply base times height repeatedly. And that's where the 18, 12, and 30 come from. Adding them all together gives me the estimated area under the curve, which is represented by that integral. All right, one more type of problem. This one is kind of like, just help you with your homework. Not a very important type of question. Another detail I want to point out, though, before I get to that is, you do want to pay attention to these endpoints. These endpoints tell us where to start and where to stop. I've seen free response questions where they give you an entire table, but since they give you x values here, like if I were to put a 1 here and a 2 here, then the question would be completely different, because then we would only be looking at this much of the table from -1 to 2. So you got to pay attention to what interval they care about by looking at the integral. I didn't do that on my problems, but I just want to give you a heads up. That does happen sometimes on the FRQs. I've seen it happen once or twice. Okay, well, here's another one. So step 1 today, you don't need to write this, but the first type of problem I gave you the graph up front. The next thing I did was I gave you a table, so you guys had to create the graph yourself. Well, now I'm going to give you one less piece of information. I'm not even going to give you the table. Instead, I'm going to give you the equation. And when I give you an equation, that means you have to find the table. And instead of using the graph, we're just going to use the shortcut. So we're going to turn the equation into a table, and then we're going to go from there. Now this question, I don't see this almost ever on the AP exam, but I did include a homework question like that, and it's possible to ask a question like this, so I figured why not, we'll go ahead and do it. But it's not a very important type of question, that's why I put it off till last. All right, so we're doing a left-handed Riemann sum of 7 subintervals to estimate this integral. They also want to know, is this an upper sum or lower sum? We'll see. If it's strictly increasing or decreasing, we can answer that, but it might not be strictly increasing or decreasing, so we'll see. All right, so where do we begin with this? What are we going to do first? First of all, let's figure out our bases. Okay? In other words, this is the thing where you're going to take your last x value and your first x value, you're going to subtract them, and then you're going to divide by the number of subintervals that they want. Now, how do I know that 10 and -4 are my last subintervals? Well, on the integral, I told you this is the last and this is the first one that you want to look at. So in this case, I've got 10 minus a -4, which is 14. And therefore, I want my bases to be 2 units long. Okay? Now, the next thing that we're going to do is we're going to set up our table. When you set up your table, you're going to put your first x value here And then based on however long your bases are, that's how much you're going to add to get to the next place. Okay, so let me show you what I mean by that. So I'm going to make a table here, x and y. You could say f of x if you prefer that instead of y. But my first x value is -4, so I'm going to start with -4. And I know that I want my bases of my rectangles to be 2 units long. So that means I'm going to go up by 2's. And you're going to keep going up by 2's until you get to your last term, which is 10. So up by 2 gives me -2. Up by 2 gives me 0. Up by 2 gives me 2. Up by 2 gives me 4. Up by 2 gives me 6. I'm running out of space, so let me be a little ghetto here. Up by 2 gives me 8, and then up by 2 more gives me 10. So I'm starting at -4, I'm ending at 10, and I'm going by 2's. So step 1 is to find your bases. Step 2 is to set up your table, starting with your first x value, ending at your last x value, going by whatever your base length is. And now you need to find your y values. So we need to figure out what these numbers are. How do we do that? You're going to plug these x values in to your equation. Okay? So for instance, if you want to know what goes here, you're going to plug -4 into your equation. And I get 0. And so that's the y value that goes here. And you're going to continue doing that. Now as for my next one, it's probably not going to come out to be a nice number. Let's see. If I plug in -2, I get 2. Now the square root of 2 is not a nice number, but that's okay. We really don't care. Just put square root of 2 there. It's good enough. I'm going to go ahead and keep doing that. I'm not going to show my work, but if you plug in 0, you would get 2. If you plug in 2, you'll get square root of 6. If you plug in 4, you're going to get the square root of 8. If you plug in 6, you're going to get the square root of 10. And if you plug in 8, you're going to get the square root of 12. And if you plug in 10, you're going to get the square root of 14. Okay? So there's my y values. The last step is calculate the area using what we've already learned. All right? So I don't have to skip any rows this time, and the reason I'm not going to skip any rows or columns, is because my table only has the ones that I care about anyway. I already went by 2's, so we don't have to skip anything. But these are all my bases, so I'm going to do base, let's see, left-handed sum, right? So we're starting on the left, and we're going to use all these heights until we get to the very last one, which we are not going to use. So it's going to be base times height, base times height, base times height, and so on. And we have our answer there. So our integral is approximately going to be 2 times 0 is 0. 2 times the square root of 2 is 2 radical 2. 2 times 2 is 4. 2 times radical 6 is next. And so on. And we don't have to simplify it. This is approximately what the area under the curve would be for this integral if we're doing a left-handed sum with 7 rectangles. And that's it. All right? So, steps. Calculate your base length, set up your table, find your y values, go to town using what we've already learned today. All right? Last one for you guys. Go ahead and pause the video here. Give this one a try. When you unpause it, you'll see the solution. All right, so here's my solution. I ended up with 3 plus 30 plus 3 minus 78. Let's see. how I got there. So first of all, you figure out your base length by doing your last x value minus your first x value divided by the number of intervals they want. Each rectangle needs to have a base of 3. So that helps me move on to step 2, where I set up my table. My first x value is -6, and then I go up by 3's after that, which takes me to -3, 0, 3, and 6. The next step is we find our y values by plugging in these x values into our equation, and I end up with those answers. Finally, since it's a right-handed Riemann sum, I start with the right endpoint, and I keep going until I eliminate the last endpoint. Doing base times height is where I end up getting these numbers, and I didn't bother simplifying because on a free response question you don't have to. Okay, and there you guys go. And so that's the end of 6.1. Next lesson we're going to talk about trapezoid sums and midpoint sums. See you then.